Welcome to the deep dive. Today, we're tackling something, well, pretty surprising in the world of large language models. For the longest time, it felt simple. More data, longer training, better models. That was the idea. But what if that's not always true? What if, after a certain point, more training actually makes things worse?
It's a really fascinating question, isn't it? Because, yeah, the conventionalism was just scale, scale, scale. We
Yeah.
sort of took it for granted.
Exactly. And this new research seems to flip that right on its head.
It really does.
So this deep dive is all about this counterintuitive phenomenon researchers are now calling catastrophic overtraining. We're going to unpack what that means, why it seems to happen, and what it could mean for AI development. And we're basing this on a specific research paper, right? It's called Overtrained Language Models Are Harder to Fine-Tune.
That's the one. Yeah, that's our mission today. And, if you've ever felt that feeling of information overload or maybe wondered if there's a smarter way to get to the core of complex topics, well, you're definitely in the right place. We're aiming to distill the really key insights from this paper for you.
Okay, good. So let's set the stage. Before this idea of catastrophic overtraining, what was the standard playbook? How did people usually train these big models?
Well, historically, it was all about scaling up, just relentlessly pushing for more data, more computing power, and crucially, processing more tokens. Tokens are basically the words or parts of words the model sees.
Right, the building blocks of language for the AI.
Exactly. So a massive token budget, we're talking trillions of tokens sometimes, is seen as the path forward. And the expectation, really the assumption, was that this always led to better performance after the model was, we call post-trained.
Post-trained, like fine-tuned for specific jobs.
Yeah, precisely. Things like instruction tuning. So the model gets better at following commands, or maybe multimodal fine-tuning, teaching it to handle images and text together. Things like that.
So it was almost like an article of faith. Feed it more, train it longer, and the final specialized model will just be better. Full stop.
That was the prevailing thought. But this research, it really shows that's not universally true. There seems to be a point, a kind of threshold, where longer pre-training actually starts to hurt the model's performance after that post-training or fine-tuning step. And that specific decline, that unexpected drop, that's what they're calling catastrophic overtraining.
Wow. And this isn't just a tiny effect either, right? The paper gives concrete examples.
Yeah, definitely not just theoretical. They looked at the Ulma 1B model, for instance. After they pre-trained it on a really extended token budget, way more tokens.
Right.
It actually performed worse on some key benchmarks after instruction tuning, like 3% worse on ALPA-CAIVL, which measures instruction following, and 2% worse on ARC, a reasoning test.
That's significant. Especially when you think about the cost of all that extra pre-training. You spend more compute, more time expecting improvement.
And you get the opposite.
Yeah.
Exactly. And what's really striking is this divergence they found.
Divergence? How so?
Well, the performance of the base model, before any fine-tuning, that does keep getting better with more pre-training tokens, generally speaking.
Okay, so the raw knowledge seems to increase.
Right. But the performance after fine-tuning for a specific task starts to drop off after that certain point. So you get this split. The base model looks better on paper. Maybe its general knowledge is wider, but its ability to actually apply that knowledge effectively after specialization gets worse.
That's the crux of it, then. A better base doesn't always mean a better final product for the task you care about.
Precisely.
And just to clarify again, when we talk about post-training here, the study focused mainly on instruction tuning and multimodal tuning, like with the LLaVA framework for vision language tasks.
Yes, those were the main focus areas in their experiments. But they do note that post-training is a broader category. It could also involve things like reinforcement learning from human feedback or technical processes like quantization or pruning to make the model smaller or faster. The implication is this overtraining issue might affect those too.
Okay, so this isn't just some weird fluke with one model or one task. The researchers found it was more widespread.
That's what they argue, yeah. They looked across several models and setups to demonstrate that this isn't just an isolated incident. It seems quite prevalent.
Which models did they dig into specifically?
They used open source checkpoints for models like Ulma 1B, the larger Ulma 27B, and also LLM 360 Amber 7B. And for the tasks, they used standard stuff. Anthropic HH and TLU datasets for instruction tuning, and the LLaVA framework for the multimodal part.
And how did they measure success, or I guess failure in this case?
They looked at it from two main angles. First, in-domain performance, or ID. That's basically how well the model did on the specific task it was fine-tuned for.
Like how well it followed instructions after instruction tuning.
Exactly. measured by things like archival score or a VLM score for the multimodal tasks.
Mhm.
And second, they looked at out-of-distribution performance, ODE. This is more about general capabilities.
Ah, so testing if the fine-tuning process somehow damaged its broader knowledge.
Sort of, yeah. They used a whole suite of common LLM benchmarks, 10 of them covering reasoning, question answering, common sense, things like ARC Challenge, PIQA, HelloSwag, Winogrand, the standard battery of tests.
Okay, so pretty comprehensive. What were the key takeaways from those tests? What did they actually find?
Well, for the smaller OLMA 1B model doing instruction tuning, they saw catastrophic overtraining kicking in once the pre-training went beyond about 2.5 trillion tokens. And interestingly, this wasn't just a drop in the specialized in-domain task performance.
Right, like the archival score you mentioned.
Yeah, that dropped. But also the out-of-distribution performance, those general reasoning and QA benchmarks, they also decreased. So it seemed to hurt both specific adaptation and general capability.
Okay, what about the multimodal fine-tuning? Same pattern.
Similar, but with a bit more nuance. With OLMA 1B, again, the overtraining effect also seemed to appear beyond that 2.5 trillion token mark. But here, the degradation was more task-dependent. The in-domain score, the VLM score for the vision language task, it didn't necessarily show a big drop at that threshold.
Oh. So it could still learn the specific new multimodal skill.
It seemed like it, at
Yeah.
least initially. But crucially, the OMOT performance, those general reasoning, QA, common sense tests, did decline, sometimes significantly. So even if it learned the new trick, its overall smartness on other things seemed to take a hit. It suggests the damage can be selective or show up in different ways depending on what you measure.
That is interesting, but you mentioned they also tested larger models, like almost 7B. What happened there?
Yeah, this is a really key point. With the larger almost 7B models, they didn't observe this catastrophic overtraining, at least not within the token budgets they tested, which went up to 3 trillion tokens.
So does that mean bigger models are just immune? Or maybe they just haven't been trained long enough yet to hit that same wall?
That's the million-dollar question, isn't it?
Yeah.
It could be that larger models have more capacity, more resilience, and the overtraining cliff is just much further out for them. Or maybe it's still there, waiting.
Okay.
Definitely needs more research.
Right. So, okay, we see this effect, particularly in smaller models tested so far. But why does it happen? What's the mechanism behind this degradation?
So the researchers dug into this why question with more controlled experiments.
Yeah.
What they found boils down to this. Modifying the parameters, the sort of internal knowledge weights of a pre-trained model, well, it causes some forgetting of what it learned before.
That seems intuitive. If you teach it something new, it might overwrite or interfere with old knowledge.
Yeah, exactly. But the key finding is what they call progressive sensitivity. This is the really crucial factor.
Progressive sensitivity, what does that mean?
It means that models that have undergone longer pre-training become more sensitive to these modifications. So if you make a change of the same size, say, during fine-tuning, a model that was pre-trained for longer will forget more of its original knowledge compared to a model pre-trained for less time.
I think I get it. It's like, imagine stretching a rubber band. You stretch it a little, it snaps back. You stretch it a lot, keep stretching it longer and longer. Eventually it becomes weaker, more brittle, and even a small extra stretch might snap it.
That's a pretty good analogy, yeah.
Yeah.
The longer pre-training makes the model, in a sense, more taught or optimized for its pre-training data.
Yeah.
It gets better at that, but it also becomes more fragile, more sensitive to being pulled in a new direction during fine-tuning.
So catastrophic overtraining happens when this increased fragility, this progressive sensitivity, causes the forgetting during fine-tuning to become so severe that it actually outweighs whatever benefits were gained from that extra bit of pre-training.
Precisely. You hit a point where the harm caused by the fine-tuning modification, amplified by this sensitivity, is greater than the gain from the last phase of pre-training. Net result, performance goes down.
So pre-training makes the model smarter in general, but also, paradoxically, harder to teach new tricks effectively after a certain point.
That's a great way to put it. The base model improves, but its adaptability degrades. It becomes overly sensitive to the noise or the changes introduced by fine-tuning.
And they connect this idea to something called progressive sharpening. What's that?
Yeah, progressive sharpening is this known empirical observation that during training, the loss landscape around the model's optimal parameters gets steeper or sharper. Think of it like a valley getting narrower and deeper. What this new research suggests is that progressive sensitivity is related, but maybe broader. It's not just that the optimal point is sharp, but the model becomes generally more sensitive to any kind of push or perturbation, maybe even more than that simple sharpness idea would predict.
Okay, so it's getting more finely tuned, but also more easily knocked off balance. Did they test this sensitivity idea directly?
They did. They ran controlled experiments that really seemed to validate it. First, they tried just adding simple, random noise, Gaussian noise, to the model's parameters, just nudging them slightly.
Okay.
And they measured how well the model retained its original knowledge using a metric called C4 perplexity. Lower perplexity is better, means it understands the language well.
Sure.
What they saw was a U-shaped curve. Initially, with more pre-training, perplexity went down, good, but then as overtraining continued, the perplexity started to increase after adding the noise, bad. It indicated knowledge loss.
So the longer trained models were more disrupted by the same amount of noise.
Exactly, and if they added larger amounts of noise, this degradation, this increase in perplexity, started happening even earlier at lower pre-training token counts.
Makes sense. What about actual fine-tuning, not just noise?
They tested that too. They fine-tuned models using a fixed learning rate. The learning rate kind of controls the size of the changes made during fine-tuning. And they found that the degradation in that C4 perplexity metric increased steadily, monotonically, with the amount of pre-training. Longer pre-training led to more forgetting during fine-tuning, confirming progressive sensitivity in a real fine-tuning scenario. And this again led to that U-shaped performance curve on downstream tasks eventually.
So multiple experiments pointing to the same underlying mechanism. Longer pre-training increases sensitivity, which can lead to performance drops after fine-tuning.
Right. And they didn't just stop at experiments. They also developed a theoretical framework. Using a simplified mathematical model, linear transfer learning, they showed how this process of incrementally learning features during pre-training naturally leads to this progressive sensitivity and, eventually, degradation.
Does the theory suggest when it's most likely to happen?
Yeah, it's just that degradation is particularly bad, or catastrophic as they call it, when the pre-training task and the fine-tuning task are somewhat misaligned.
Misaligned, meaning they require different kinds of knowledge or reasoning?
Kind of, yeah. If the fine-tuning task pulls the model in a very different direction than where pre-training was taking it, that's when the sensitivity really causes problems.
Okay, this leads to a really practical problem then. There seems to be this inherent trade-off.
Exactly. You can try to lessen the degradation. For instance, you could use really small learning rates during fine-tuning, make very gentle adjustments.
Right, be less disruptive.
But the downside there is, if you're too gentle, the model might not learn the new fine-tuning task effectively. It won't adapt enough.
So you might preserve the general knowledge, but fail at the specific task you wanted it to learn.
Precisely. It's a balancing act. And finding the optimal learning rate for fine-tuning becomes really critical. The paper notes that how this optimal learning rate changes as pre-training increases can actually determine where you see the degradation, whether it shows up more in the in-domain performance or the out-of-domain performance.
Ugh. This feels like it really challenges some of the basic assumptions we've had about scaling laws in AI. You know, those laws that predict performance based on model size, data size, compute.
It absolutely does. Those scaling laws might hold true for the pre-trained model's capabilities, but they might not accurately predict the final downstream performance after fine-tuning, especially if you push pre-training into these overtraining regimes. It suggests that maybe, just maybe, stopping pre-training earlier, using fewer tokens than what seems compute optimal based on scaling laws alone, could actually lead to a better fine-tuned model in the end.
That's a huge implication, especially for people developing smaller, more efficient models. They might be tempted to just keep pre-training.
Right, thinking more is always better. But this research suggests there's a point of diminishing or even negative returns for fine-tuning adaptability. You might be better off stopping sooner.
Okay, let's try to wrap this up. What's the big takeaway for everyone listening and for the field?
Well, I think the biggest thing is that the simple mantra of more is always better for pre-training language models. It's clearly being challenged. It's not that straightforward.
Yeah, we've seen how this catastrophic overtraining can make models too sensitive, too fragile when you try to specialize them later, and they can end up performing worse on the very tasks you care about.
It really shifts the focus, doesn't it?
Yeah.
Optimizing these models isn't just about raw scale anymore. It's maybe more about finding that that sweet spot.
Right, where the model knows a lot, it's deeply knowledgeable, but it still has the flexibility, the plasticity to learn new things effectively.
Exactly. It highlights this really delicate balance between just acquiring broad knowledge and retaining the ability to adapt and specialize.
So as we keep building these incredibly powerful AI systems, maybe the next big leap isn't just making them bigger, but making them, I don't know, wiser.
Wiser, I like that.
Yeah.
Knowing when to stop learning the general stuff, perhaps, and figuring out how to maintain that adaptability throughout the process.
It definitely makes you wonder what kinds of new training methods or paradigms might come out of this. Ones that prioritize not just scale, but intelligent, adaptable knowledge. That feels like a really interesting question to leave people with.
Absolutely. It opens up a whole new avenue for research and optimization. Finding that balance is key.